Alright, so today we are happy to have Sherwin from the University of Cambridge giving the seminar. He's a university lecturer. He did his PhD in Princeton, was status critical before moving across the continent to Berkeley, where he was first a Miller Fellow, and then Einstein Fellow. Last year he started his appointment in Cambridge, and with the appointment there is another fellowship, Rutherford Fellowship, so it's one fellowship after another. Blake has been an instrumental part of the CMB lensing analysis group in both AdvACT, and all the informational of ACT and Colorado, including being one of the leading authors on the paper which provided the first detection of the CMB lensing effect in the CMB data only, which means without using external data from Cosmology. He was also part of the team that did the first CMB delensing analysis, which is a technique that shows a great potential for the future. As part of the Simons Observatory, CMB Stage 4 and Lightbird, Blake will continue to be one of the driving forces of the CMB lensing, and so today he will tell us a little bit about the future of the great. So without further ado now, join me in welcoming Blake Sherwin.
All right, thanks for that nice and very comprehensive introduction and the invitation to speak here. I'm going to be talking, as you heard, about CMB lensing and what it can tell us about fundamental physics with, in some cases, some new approaches. And so I'm going to start very general and get rapidly more specialized. Please feel free to interrupt me at any time. It's much more interesting that way. All right, so let me just start with a little bit of background to this field that I'm sure most of you know very well. As you know, we can look out into the universe and see hundreds of billions of galaxies in modern astronomical surveys, and we can see an enormous amount of matter in stars and in gas. But all of this visible matter, as you know, makes up less than 20% of the mass in our universe, and more than 80% of the mass in our universe is made out of invisible dark matter. But as you also know, this dark matter is not uniformly distributed, we believe, but instead forms kind of a filamentary scaffolding that underlies the distribution of galaxies. And in this simulation, you can see what our current picture is for what this looks like. So it would be really interesting if we could directly and precisely actually just map out all the distribution of mass and dark matter in the universe, not just because, this dark matter is really responsible for our existence because its gravity is crucial for driving the formation of galaxies and all visible structure, but also because how the dark matter is distributed and how the mass is distributed contains an enormous amount of information on some of the key open questions in cosmology and in fundamental physics, and in a way that our theories can calculate, right? Unlike galaxy formation, et cetera, this is a much easier problem to figure out how dark matter clusters. Okay, so first to remind you about some of these key open questions, just for the few of you who haven't thought about cosmology much at all. On the one hand, us cosmologists should be really happy and very proud of ourselves because we have this beautiful, amazing cosmological model, the standard lambda CDM model, which involves a fast expansion in the early universe and inflation, the formation of structure driven by dark matter, and the fact that dark energy kicks in and accelerates everything apart. And we should be really happy because we have this model that just has 6 free parameters, and we can fit CMB data and large-scale structure data and all these different data sets with thousands of degrees of freedom to sub-percent precision. So that's all great. But on the other hand, we have no idea what's going on, right? We've just sort of figured out how little we know and written down parameters where we have ignorance, right? And so this motivates some of these big questions, why we want to precisely map and figure out and reconstruct the distribution of dark matter and mass, because it contains and encodes an enormous amount of information on some of these key questions. For example, what is the physics of inflation in the early universe? What are the properties of particles in our universe, such as neutrinos? What is dark energy? And in particular, is it dynamical? Is it time evolving? Or is it a cosmological constant? And then finally, and not trivially, is our standard cosmology correct? Does it correctly predict how structure grows in regimes where we haven't really probed at that exactly, for example, at very high redshifts? Okay, so now how can we map out this invisible distribution of mass and dark matter? The best way that we currently have of doing this directly is using gravitational lensing, which you're all familiar with, gravity from all matter, including dark matter, will deflect radiation as it passes by. And that's how we can see and infer the presence of dark matter. Now, in my talk, as you know, I will discuss the gravitational lensing of a very special source of radiation, cosmic microwave background, and sort of the afterglow of the Big Bang, if you're giving a popular talk. Here you can see this beautiful image of the Planck satellite showing the patterns, the anisotropies in the brightness, or equivalently, the temperature. Now, this cosmic microwave background is really a unique source for the study of gravitational lensing. Right? And the reason for that is it's the oldest source of light we can see, and that means it's been traveling for the longest. It's the most distant screen, the most distant source that we can possibly observe. And so what happens when the photons from this most distant screen are emitted is that they travel through the entire observable universe and the entire observable distribution of dark matter. And along their paths to our telescopes, they're gravitationally deflected by the entire mass distribution through which they pass. Right? And this leads to a net remapping of the observed CMB sky. And in a simulation, I can illustrate this. So here is a 10 by 10 degree simulation, a cutout of the CMB with lensing switched off. And now I can switch the lensing effect on. And it's not the most dramatic effect ever. It's just a remapping by a few arc minutes. And the fact that this is this tiny remapping to these fluctuations that are already at the level of a part 10 to the 4, illustrates why it is that we've only recently been able to see this stuff. It's absolutely tiny. Okay, so I don't think this picture is that intuitive, these tiny remappings. So I always like to show sort of a cartoon picture where I dramatically exaggerate the size of the effect. So what I'm going to think about is having a big blob of, again, starting with this background unlensed CMB. And I'm going to put an enormous blob of dark matter in front here. And so what does it do? Well, it deflects the radiation around this clump of mass and dark matter and magnifies the background CMB fluctuations. Okay? So the CMB behind a clump of mass or dark matter gets stretched out and sheared in this characteristic way. And this I can use to define an observable. All right, and this observable is the lensing deflection field. It's a two-dimensional vector field that points from where the CMB photon is emitted to where it's ultimately received. Okay? Now, I've said that this is an observable, right? But how can I actually observe this, right, when I don't just have a simulation and I can't flash back and forth? Well, the intuition is actually really simple for how I can observe this lensing deflection field. Basically, in a very hand-waving sense, all I have to do is look for these stretching features and measure their strength, and that tells me the strength of the lensing from the CMB pattern. In a little bit more detail, what I could imagine doing is locally measuring the power spectrum and plotting it in a sort of a 2D plot, Fourier transform in the y and x direction. And I can just look at how much this known standard object is deformed. How much is it locally stretched out and sheared, just like a galaxy is stretched out and sheared in galaxy lensing. And then quantitatively, I can go from the CMB distortion to a lensing deflection field. That's kind of the intuition. Are there any questions about the intuition? Yeah, good. All right. Now we'll talk about what we actually do, which I promise is actually the same as the intuition, even though it's not totally obvious. But you can show that it's the same. All right, what do we actually do? Well, this local distortion is really a violation of statistical homogeneity, right? The statistics, when it's distorted, are not the same from place to place. And what that mathematically corresponds to, if I break homogeneity, means that there are now correlations between two different Fourier modes of the CMB temperature, T of L and T of a different L, that used to not be there. Okay? So there's 0 if it's statistically homogeneous. But now lensing correlates these modes that used to not be correlated. And so that tells you, well, this is how I should measure lensing. Using, a basic idea is, well, I'm just going to write down a pair of these modes and look at how correlated they are. And the strength of that correlation, summing over pairs, gives me the lensing. In this so-called quadratic estimator, right, it's a quadratic in the temperature. Okay, so this is how we've measured it so far, and for the near future at least, we're going to continue to measure it this way. All right, what does lensing tell us? Why is it worth doing this? Well, if we measure the lensing deflection field, we've directly and gravitationally probed the projected density of mass, most of which is dark matter, projected with some kernel all the way from here to the last scattering surface. And I think that's just really, conceptually kind of amazing, because if you think about the volume of the observable universe, this is sort of more or less to scale. Galaxy surveys have really in detail mapped out the local universe below redshift 1. But actually, there's an enormous amount of volume that just actually hasn't really been probed or explored. And we assume we know what's going on, but we haven't really mapped it out in detail. And so, what I think is actually just really neat is that CMB lensing probes the projected dark matter all the way back across this mostly unobserved and unmapped volume. And so, as I'll explain, we are going to be making, over the next decade, really high precision maps of lensing over a significant fraction of the sky with really low noise. And so these lensing maps, this is just a cartoon, these lensing maps, these high precision lensing maps will really be maps of nearly all the dark matter and mass in the universe. And I think it's just really cool that over the next decade we'll be able to map all the mass that there is. But the reason we're doing that is not because it's neat. The reason we're doing it is because these sort of high precision, large sky lensing maps are going to be really powerful probes of fundamental physics and cosmology. And the way this works is very simple. Lots of different kinds of unknown physics affect how structure grows in our universe, and therefore affect the appearance of this lensing map. Different kinds of exotic physics will have different kinds of perturbations in them, and will have different contributions to the Hubble expansion, and therefore the Hubble drag, when you're thinking about the growth of structure. And therefore, they'll just lead to a different appearance of this kind of lensing map. So there are lots of interesting kinds of physics that you can probe with the appearance of a dark matter map, or in projection, a lensing map. And you could talk about early dark energy, you could talk about axions, you could talk about constraining modified gravity. But I'm going to focus on neutrino mass in the first part of my talk, because it's something that we know is there and we just have to go look for it. All right, so that's what I'll turn to now, measuring neutrino masses with high precision lensing spectra. Okay, so why is this an interesting problem? Well, neutrinos are 3 of the 12 fundamental fermions that we have. And we know that they have mass from oscillation experiments. But there's an enormous amount of physics that we just don't understand. All right? So we don't know the absolute scale of the neutrino masses. We don't know whether there are 2 light neutrinos and 1 heavy one, or 1 light one and 2 heavy ones. We don't know whether neutrinos are their own antiparticle or not. Are they Majorana fermions or Dirac fermions? And really the big question is, what is the mechanism that explains how neutrinos get their mass? And why is it that neutrinos, through this mechanism, end up with a mass that's so much lighter than that of any other particle that we know? So what we can do in cosmology is measure the sum of the masses, okay? The sum of the 3 neutrino masses. And if we can measure this mass sum, we can get insight into some of these questions. So directly, we'll know the scale. Okay, we'll know the absolute scale of the mass. It's a new scale in physics. It will determine. We could, if we're lucky, determine the mass ordering, if it's normal or inverted. And what I think I've learned a bit more about recently, I think is very interesting, is that we can set targets for terrestrial decay experiments that could help us figure out whether neutrinos are their own antiparticle or not. So we'll set a target, and a neutrinoless double beta decay experiment will look for it, and if it doesn't find it, we could say neutrinos are not their own antiparticle. And so I really think the most interesting thing is that this is part of a big program of understanding neutrino physics, comparing cosmological measurements with lab measurements and just seeing if everything is consistent, whether there's new physics, and how it works. Okay, so how can we probe neutrino masses with cosmology? Well, the reason we can probe neutrino masses with cosmology is because, again, it affects how structure grows. And so here's how it works. On large scales, neutrinos are just like cold dark matter. They don't interact. And so they clump and cluster in the same way as cold dark matter. But on smaller scales, you notice the fact that neutrinos actually are moving around very quickly. And so this prevents them from collapsing and clumping. And yet they still have an energy density. They still are contributing to the Hubble expansion. And so the fact that they don't cluster and clump, but do still cause the universe to expand and give you this extra Hubble drag means that it actually suppresses the fact that you have neutrinos that have mass and energy suppresses the formation of small-scale structure. So on the right, you can see the distribution of dark matter. If I have a lot of energy in neutrinos, a lot of mass in neutrinos, and the small scales are really suppressed. They're blurred out compared to what it would look like if neutrinos have no energy and no mass, and you can totally neglect them. Okay, does that make sense? All right, so basically all we have to do is go along, map all the dark matter in the universe, and then we can figure out how blurred out it is and determine the unknown mass, the neutrino.
What's the optical depth for one direction with the neutrino, right? We have the cross-section of the 10 to the minus 40 centimeters squared.
This is all gravitational, right? This is not a direct interaction through the weak force or something like that. So this is all just the gravitational effects of the neutrino perturbations and their contribution to the background expansion.
How much of the energy that you have in neutrinos compared to like other baryons?
It's like a little bit less. So it's like a few percent of the CDM density. So but it's still appreciable, right? It's not completely negligible.
Smaller mass compared to baryons. Whether they have.
Well, that is exactly the key question, right? I mean, we have to figure out the mechanism. We don't know the mechanism. There's some ideas about seesaw mechanisms, how you could have one very heavy particle and one very light one, but we don't know the details, and we need to figure it out. And it's a big question. Because there are a lot of them around. They're a huge number.
The mean density is 112 centimeter. The mean density baryons is 7.
Yeah.
They're 9 times more neutrinos than they are baryons, so they weigh less. Still less, but not quite as much less.
Yeah. No, so it is really weird, right? Why are they so light? Very strange. Okay, so we want to go out and measure the neutrino mass, which we don't know, by looking for how much fine features in the mass distribution are blurred out. Okay, so what do? We take a CMB temperature map or a CMB polar. Yeah?
What is omega neutrino right now? How well is it?
Sweet.
What kind of aircraft?
Factor 2. Sweet. Depending on the L you take.
Yeah.
Sweet. 4.
Between 2 and 3. Okay. So, well, jumping ahead, how well do you measure?
Well, I'll discuss this in a lot of detail. You'll know exactly how well we can measure it. Okay, all right, so how do we measure? What we want to do is measure a map of lensing. What do? We take a temperature map, and we apply these fancy quadratic estimators or other, even fancier estimators. We spend years worrying about various systematics, such as all these other astrophysical sources that Alex just gave a really nice talk about. Point sources, SC clusters, CIB, etc. Worry about how much they mimic lensing. I won't talk about this in detail unless you ask me about it. And then we get a map of the CMB lensing. Okay? So this is a map, and the color scale tells you how strong the lensing is. All right? And so that means the stronger the lensing is, the more sort of projected dark matter I have behind this, in this direction. Now, of course, when I want to do something very precise, like measure the neutrino mass, I don't want to just look at this fundamental object, the map of lensing. This is one of the earlier ones we made with AdvACT, actually. We don't want to just look at it and say, oh, this looks pretty blurry to me. We want to do this quantitatively. As usual in cosmology, when things are close to Gaussian, we measure a power spectrum. Okay, so this power spectrum is really a key observable, the lensing power spectrum, CLDD. And what it tells you is, it tells you how strong the lensing is as a function of the angular extent of the lens. Okay, so how strong is lensing versus angular extent of the lens, where this is sort of an angular wave number. So small scales are on the right. And so by quantifying in this way, we can make predictions. We can predict what does lambda CDM tell us, how big should lenses be as a function of their angular extent. And we get this nice black lambda CDM theory curve. And we can predict other non-standard physics. Well, I guess this isn't non-standard, but for example, neutrino mass suppresses small features in the mass distribution, and therefore it shows up as a small suppression of the lensing power spectrum, which is just the projected matter power spectrum. Okay, so when Alex and I started working on this stuff, we hadn't found this, but when we were young and naive and had all our futures ahead of us, we set out to go off and measure these lensing power spectra for the first time. So Alex was working on SPT, and I was working with Sudeep Das on ACT. And so a long time ago, we measured these points, these green data points, which were the first detection, as Pavel mentioned, of this lensing power spectrum. And yes, the significance is pretty moderate. It was just a few sigma. But I think it's worth bearing in mind that it's pretty cool that our model, our lambda CDM model, can correctly predict how big the structures and blobs of dark matter are halfway across the universe, right? That's a non-trivial accomplishment that our lambda CDM theory now has met, starting with these first detections. But what's really impressive is just in 5 years afterwards, this field has advanced from these first detections to be the best way that we have, I think, in terms of pure signal to noise, of measuring weak gravitational lensing. So here you can see this sort of state-of-the-art Planck lensing power spectrum. There's actually been a slight update. I should have updated that. So in a few years, we went from first detections to sort of a high-precision probe. But what's exciting is that, hopefully at least, this is only just starting, right? And the reason is not just that we're getting smarter and better at doing these sorts of lensing analyses, but perhaps the main reason is that CMB experiments are getting much better very quickly. So if you look at this plot of sort of CMB experiment noise level as a function of year, you'll see kind of, given this as a log plot, really an exponential improvement going from WMAP to Planck. And this improvement is expected to continue with ACT, and advanced ACT and Simons Observatory, and then ultimately CMB stage 4 over the next decade, right? These are all ground-based CMB experiments. Here you can see ACT in the middle surrounded by a ground screen. So Alex and I have recently been working on ACT-Pol. So I'll talk a little bit about ACT-Pol, what we've been doing recently and now, and then I'll turn to the future with Simons Observatory, just for a few slides. All right, so recently we upgraded our pipelines, the earlier ones from ACT, wrote new, faster polarization lensing pipelines, and made much nicer and much bigger maps of the dark matter. This one is something like 50 degrees across, compared to the older, smaller ACT lensing or dark matter maps. And from our early ACT-Pol data, we reported a more precise measurement of the lensing power spectrum. It's still not quite as good as Planck, but here you can see our results from a few years ago in red, and again they were consistent with lambda CDM, and we were able to get a constraint using just our data of around 0.2 eV at 1 sigma. So we just put an upper limit on the neutrino mass. But what's exciting is that this is just a very small fraction of what the data that we have right now. Okay? So this is something, I think, less than 10% what we have in the can right now. So here is the lensing map that we made like 2 years ago. And this is the CMB data that we have, just showing how much we've observed. All right, so we have these enormous CMB maps now that cover more than 15,000 square degrees of sky. So here again, showing the footprint. Here's the galaxy. Here's the sort of full sky. So we have a lot of data with ACT over a lot of the sky. Now, the quality varies a lot. In some regions, it's actually noisier than Planck still. In some regions, it gets incredibly deep, below 10 microkelvin arc minute. And so Alex and I and other collaborators from ACT are working very hard on getting this big data set analyzed and out the door. So one thing you can do is make lensing maps and cross-correlate them. And my new graduate student as of last year has been making these sort of nice new lensing maps. And just from a very small subfield, you're actually getting really nice lensing maps, and which you can illustrate by, for example, cross-correlating with infrared galaxies. And I don't want to, you shouldn't look at this too hard, but it just is supposed to illustrate the high precision that we're getting with data right now. Ultimately, what we're going to do is measure, using cross-correlations, tomographically the growth of structure as a function of redshift to constrain things like dark energy. Something that Alex is leading, and that we're working very hard on getting out the door as well, is the sort of next ACT lensing power spectrum with the data set that we have in the can now. And so this should be around 3% precision, as you can see in this forecast here. And the cool thing there is it's as precise as Planck, and it's completely independent. So we should be able to provide an independent cross-check of Planck on a comparable area of sky, maybe not quite as large sky area. And so any claims of tensions in the amplitude of structure, and independently H naught from this measurement, we should be able to test. So I think that's going to be really neat. We can have an independent test of Planck with data that we have right now. And also place really nice constraints on things like the neutrino mass. But that's just sort of what we have right now. Let me turn a little bit towards the future of these sorts of measurements. What was that?
You still didn't put an error bar on the rest.
On this one?
Yeah.
This is the error, right? So that's the error, and we know it has to be at least 60 millielectron volts. Okay, so it could be a lot larger, and we could detect it, significantly then. But yeah, we're closing in on the place where we have to see it, and we're not that far off right now.
So
Yep.
Planck was measuring it at 2.5% precision.
Something like that. It was like 40s.
Why would you? So this seems better than Planck, right? Than your neutrino mass constraint, your forecast neutrino mass constraint.
Not much better, right? It's like sort of comparable, like 0.12. Yeah, 2 sigma.
And the other nice thing is it's an independent set of L codes, so the Planck measurement only goes up to L 400.
Yeah.
Right. Okay, so that's why it was.
Yeah, I think actually our measurement will always look a lot nicer because we have these tiny error bars at high L, but the signal is getting very small. But if I just think about, if I'm agnostic about what the power spectrum should look like, it's actually very precise, very small angular scales. Yeah. Okay, so this is what we can hopefully get out. And then Alex, when? Next few months? Something like that. Okay, all right, good. Yeah. It's going to be great. Okay, now let's turn a little bit towards the future. First of all, we have advance ACT, an upgrade to ACT, which should push us even further still. But let me just go a little bit further towards Simons Observatory. And I'm sure a lot of you know about Simons Observatory. But what Simons Observatory is what happens when Jim Simons gives you $50 million and as the ACT collaboration asks you to merge with the Polar Bear collaboration and a few other collaborators. And obviously, Renee is not just playing a big role in ACT, it's also in Simons Observatory, as is Alex. And yeah, so what was fun over the last 2 years is we got to do a lot of work on the lensing group on optimizing our science, right? On figuring out how can we get the best lensing science, how should we design this experiment in order to really get as much as we can. And so what we are going to do then is build one 6-meter large aperture telescope, and then a bunch of something like 3 small aperture telescopes that will go after inflation science. All right, so we're building an array of telescopes in the Atacama Desert, as you can see here from this picture. Just to illustrate the size of these sorts of large aperture telescopes, here's the design of the large aperture telescope. Sort of a 6-meter mirror, sort of 2 mirrors, and it goes into an array, a receiver with arrays of very, very sensitive transition edge sensing bolometers. So here, just for scale, is a Boeing 737. So this thing is going to rotate around, and I'm glad that I don't have to build it, because it sounds hard. Okay, right. So why is this so exciting for lensing science? Well, these sort of Simons Observatory, large sky, low noise, high resolution CMB maps will be amazing for lensing science, right? So if you look at the raw forecast, you can expect well below 1% precision on these lensing power spectra. And these measurements are, I would argue, very clean and very robust. They rely on sort of near linear physics, have a very well understood source screen, right? And so we really, I think, understand them very well. And so any physics that changes how structure grows over a wide range of redshifts will show up here. Right? So if something breaks at redshift 4, we will see it. But most, what we know for sure is that we will be able to get a very competitive constraint of order 20 to 30 millielectron volts, depending on what our tau constraint is. And so even in the most pessimistic scenario, we'll see the neutrino mass at a few sigma. But if it doesn't have to be the minimal one, we could get lucky and it could be a lot more significant. So this is, of course, what the forecasts tell you. And as anyone who's worked on data knows, that there's an enormous amount of work that we have to do in order to make this a reality, right? We have to do an enormous amount of work on systematics control, on better estimators, and on understanding not just extragalactic, but also instrumental systematics, lots of other things like that. Even our theory needs to be pushed to higher precision, taking into account higher order effects and other complications that we haven't calculated like that. So that's a major area that I think we're going to be working on over the next few years. One thing that I think is kind of neat, and I think it'll just be an aside, is that I think a lot of the developments that we've made in CMB lensing analysis in theory will actually be applicable to other areas. And this is, I know, something that Whaley has worked on a fair bit. We can measure and reconstruct lensing from these two temperature fields. And it turns out that that's closely related to the fact that there's a bispectrum between temperature and CMB lensing. So you can look for other situations that are very similar. For example, I could reconstruct the linear density field from a quadratic estimator in the galaxy field. This is something that I'm working on with Simon Foreman, actually. Or something that I worked on with Alex is that you can reconstruct the dust B modes on large scales, we think, using the small scale temperature. So a lot of these sort of tools of quadratic estimators, bias hardening, a lot of this technology I think will have broad applicability towards reconstructing fields that you care about a lot using other fields that are connected through a 3-point function. Please ask me more about this. I don't really have time to discuss it. But going beyond the quadratic estimator, something that I think is going to be really exciting is, maybe these forecasts are not optimistic, but maybe they're actually a bit pessimistic. Because maybe with this much better data, we can actually measure lensing a lot better. And so that's what I want to talk about now. Could it be that we've actually even been underselling what we can do? Maybe. We'll see. So why do I think that maybe we could measure lensing better than we have thus far? In particular, in temperature. And I know some people here have also thought about this a bit. So the standard lore until a few years ago was that in polarization you can do fancier things in the quadratic estimator, and those will improve your constraints. But in temperature, the quadratic estimator is it. You can't do better. There's nothing more you can do. But so Simona Ferraro and I and Ben Horowitz and others started thinking about this, and it seems kind of weird. And here's why we thought that was weird. Because if I look at the lensing signal and I plot the noise curves that I can get from the quadratic estimators, the noise at high L on small angular scales seems to blow up. So it looks like you can't ever measure these really small scales very well. On the other hand, if you're just really dumb and you don't think about it and you just look at not the lensing power spectrum, but a much more basic observable, the CMB temperature power spectrum, a well-known result in CMB is that if I look at very high L on small scales, the CMB temperature power spectrum just turns into the lensing power spectrum, right? Just plot from CAM and you'll see that it just turns into the lensing power spectrum. So how is it possible that this apparently ideal estimator for temperature has huge noise, and yet if I'm not nearly as smart and I just look at the high L temperature power spectrum, I can just read off all of these high L lenses that I shouldn't be able to see. So I think what we concluded is that this suggests that there's a much better estimator that's there on small angular scales in temperature, which I think people hadn't appreciated. And the reason physically this is true is just because the small scale CMB gets incredibly simple. So this is a little bit technical. If you don't follow this, just don't worry. We'll get back to more basic stuff soon. If I look at a normal sized lens, a pretty big lens, there's a lot of structure behind it, a lot of fluctuations. On the other hand, if I zoom in to a really tiny lens, because of the silk damping, this diffusion, the CMB becomes really smooth if I zoom in onto very small scales. And it just looks like a gradient. Now, if I think about this sort of small scale CMB, and this is the lens CMB here, it's just related to the unlensed CMB by this remapping, right? This is the lensing deflection field. So what I could do is I could Taylor expand in small deflection angles. And if I'm looking at really small scales, actually, the background CMB has diffused away. It's totally negligible, and I'm going to neglect noise in foregrounds. So all I have is that the measured small scale CMB is incredibly simple. It's just the lensing times the size of the local gradient. All right? So on small scales, everything is super simple. What I see is just lensing times this gradient. So this is actually almost an embarrassingly basic idea. How can you measure lensing in the super small scale limit? All I have to do is just take the CMB and divide it by this local gradient, which I can actually measure very well, right? I can just smooth the CMB and take the derivative, and then I know this. So this is what we call the sort of gradient inversion estimator. This is actually one of the first ways that people thought about measuring lensing. I take the CMB, I divide by the local gradient, and that's it. And you can show that this is actually the optimal estimator in this small scale limit. So, all right, so this is, what was that?
This is like Newton-Raphson method. So if you follow it, we'll take it to the lens.
So this is, I wouldn't even necessarily say this is a Newton-Raphson method. The quadratic estimator, yeah, it's not obvious to me in what way this is a Newton-Raphson method.
So you divide the value by the derivative. So it seems to me that if you follow the trajectory, we take it to the center of the lens.
It could be, I know what you mean, it looks like a step here, but it's not clear to me what optimization calculation you'd be doing that would give you this Newton-Raphson step. There's some other, actually the quadratic estimator is usually thought of as a Newton-Raphson step in the likelihood, the first Newton-Raphson step in the likelihood, but at least to me it's not clear what this Newton-Raphson step is of. What is the optimization problem? It's a good question though. Maybe you can think about this in an interesting way. Okay, so this is what we're proposing to do. Super simple, take the temperature, divide the gradient out. But we can now see what we've been doing wrong with this quadratic estimator. We can prove this is the right thing to do. What we've been doing in this quadratic estimator is instead of dividing by grad t, multiply by grad t, and then divide out the RMS grad t. So you're always making, even though on average you'll get the right answer, you're always kind of multiplying by an error that's of order the RMS gradient. So you're adding extra cosmic variance. This is what we pointed out a while ago. Over the last year or so, I've been working with a really good master's student at Cambridge who's now doing a PhD at Harvard. And we tried to extend this idea to actually be able to make a continuous large-scale lensing map and measure lensing power spectra. And the thing that's a little tricky is you have to go away from the gradient being constant and allow it to vary, but just very slowly. Right? So there's a lot of tricky stuff there. Something that's sort of neat is that you expect the noise to depend on the size of the gradient. The bigger the gradient is, the bigger the signal is. Right? So how well you can measure lensing depends on what the background CMB happens to look like. If there's a big gradient, the signal pops right out. And so I'm not going to go into details here, but we spent a lot of time sort of figuring out how we can weight this properly and take into account the fact that the gradient is actually very slowly varying. But we have this new estimator now that allows us to make small-scale lensing maps. And I think they're better than what we've been able to do previously. So to illustrate that with the simulation, how we can sort of do better on small scales, here you can see the right answer, a small-scale simulated lensing map. And here you can see what the standard approach gives you. It's all noise. This is our new method, and in some places it's noisy, but wherever there's a big gradient, you can actually see the signal. And if you correlate your reconstruction with the right answer, you get exactly the right correlation coefficient. So it's highly correlated. Yeah?
So that map on the left looks really non-Gaussian to me. Am I imagining that?
I think it's Gaussian, just like filtered. It's been filtered at very high L's.
Because there's some spots where there's a lot of variance and other spots where there isn't.
Yeah, unless I mislabeled that plot. But I think that should be a Gaussian field. That's a good point, though. All right, we'll look at that again. Anyway, so basically you can make these better lensing maps, we think, on small scales. And they're actual continuous maps. And now the question is the error bar for things like a lensing power spectrum smaller? And it looks like yes. So Brianna simulated this. So here's the set of standard error bar on using the standard method. This is binned and delta L of 200. And it looks like at very high L, we improve things by a factor between 5 and 10, which is actually, given that these forecasts have already been very impressive, the fact that you can do still better, I think, is pretty exciting. All right, any questions about this? Yeah?
Point sources.
Yes, so that's a very good question, and I know some people here have thought a little bit more than we have actually about this. One of the big problems if you're trying to do this in temperature is foregrounds, right? And so the standard answer is you would just do this in polarization. And the same thing works for Q and U. But it could be that you're OK, because I think the foregrounds are not correlated with the gradient. So it could be that they just add noise. But we have to look at that more. We also have to think about what exactly is the best thing to constrain in this way. I know Renee has thought a lot about axions, and I think this might be a nice target for that. We talked to her briefly about this. But, and then I think a really cool question is, this should be in a maximum likelihood approach. But somehow it hasn't been appreciated that this has to come out. And so there should be one procedure that works really well on all angular scales. So we understand the mathematics here. So why is it that we haven't been getting this out? OK, so I think it's really exciting that we have all this great data, and it could be that there are more opportunities for science than we had thought. All right, in the last bit of my talk, the last 10 minutes or so, I want to completely switch gears. All right, so I hope I've convinced you that this is an exciting field to be working on because we can make these really nice lensing maps with all this great data, and we can use them to learn about the neutrino mass and lots of other kinds of cool physics. So from that perspective, lensing is this fantastic signal that we should be really happy to have. But in the last bit of my talk, I want to take a really different perspective, which is that if we're interested instead in the early universe and inflation, lensing is really horrible and annoying. And it's really a bummer that we have it, because it kind of blurs out and obscures our view of the early universe. OK, so let me just talk about that. First, to motivate the study of the early universe, I think is super easy, because everyone wants to know, what happened at the beginning of the universe. In a little bit more detail, what blew up the universe and set up the first seeds of structure that over billions of years turned into the galaxies and stars and planets and people. So of course, as you know, we have a really nice idea. I think it's a really beautiful idea for how this happened. I'm sure you're all familiar with it, inflation, right? Which is a mechanism that was designed to blow up the universe and make it flat. But at the same time, maybe by accident, I've heard the history as it was sort of by accident, it creates the initial differences in density, the seeds of structure, in a really amazing way, because it blows up sort of primordial quantum vacuum fluctuations in this inflaton field and makes them real. And these then grow into galaxies, right? So in inflation, you're here because of a random quantum fluctuation in the inflaton 14 billion years ago. I don't know if that's a nice thing or not. OK, so now of course, we do have very good evidence for this idea just from the normal standard scalar density perturbations. But we don't really know it for sure. And in particular, we don't understand the physics in detail, the microphysics of inflation at all, I would say. We don't know what is inflating. The nice thing is there is one extra prediction that comes from inflation, is that some many of the simple models make a detectable level of inflationary gravitational waves. And so if we could find these inflationary gravitational waves, first of all, we would confirm that inflation indeed happened. But perhaps more interestingly, we would actually learn about the physics that made it happen, because we would directly learn about the energy scale of inflation. If we measure the strength of this sort of background, parameterized by the tensor to scalar ratio r, it tells us about this energy scale. It also tells us about the derivatives of the potential and about how far this field moved in field space. So by detecting inflationary gravitational waves and measuring their strength, we'll confirm inflation, and we'll learn a lot more about its physics. Okay, so what's the best way of doing this? I'm sure a lot of you have heard about this before. The best way, to my mind at least, is to look for a characteristic pattern in the CMB polarization that inflation induces. And this pattern is called B-mode polarization. All right, so just a lightning review of this observable. The CMB is polarized at the 10% level, and polarization fields have 2 degrees of freedom, a magnitude and a direction. And now I can rearrange these 2 degrees of freedom into 2 other ways of writing them: the E-mode field, an E-mode pattern, and a B-mode pattern. And the reason this decomposition is the one that you care about and want to use is because the stuff you don't care about, the boring stuff like scalar perturbations and planets and stuff, only makes, that's not true, the normal scalar physics, it's not exotic inflation stuff, only makes E-mode polarization. Whereas inflationary gravitational waves make both, right? It doesn't just make E-modes, it also makes B-mode polarization. And so if I look in the B-mode polarization, I have no background from the stuff that, from a fundamental physics perspective at least, we already understand. That's all locked up in E-modes. And so that's why this is a major effort in the next generation CMB experiment. It's because if you measure this B-mode, you can see even small levels of inflationary gravitational waves really clearly without any background from the stuff, the boring stuff. It's not actually boring, of course, I'm just kidding, that we already understand, right? So it's a null channel. Now, the problem with that is that I've sort of lied, because there's other stuff that we, from a physics perspective, think of as non-primordial that also makes B-modes, okay? So for example, galactic dust, we learned from the bicep results, if not before, also makes B-mode polarization. But that problem is a huge, that's a big challenge, but we think that with data at different frequencies, we can solve this, this problem. But there's, in a sense, maybe an even more fundamental problem, I don't know, which is that lensing also makes B-modes, all right? Because lensing deflects a pure E-mode pattern and turns a little bit of it into B-modes. So this big problem then that we're starting to face is that we now have this lensing B-mode background noise that obscures a small inflation signal from the early universe. And so this has already begun to limit constraints on inflation. But in the future, this is going to be a huge problem. And just for fun, I want to illustrate how much of a problem lensing is going to be for future inflation studies, looking at an experiment beyond Simons Observatory, CMB stage 4, and plotting the error on R, the inflation signal strength in arbitrary units. So, without lensing, it should be really well constrained. Very powerful experiment. If now I add lensing noise, it blows up the error by a factor of something like 25. All right? So we need to be able to get around this enormous lensing background if we want to make progress for future surveys. And indeed, we do really want to make progress, because actually the next few orders of magnitude, we can push our constraints down. Even if we don't find anything, we'll have ruled out a very interesting class of so-called large field inflation models. Okay, so how can we get around this lensing background noise? Well, luckily we have a very nice method for doing this. It's called delensing, and the idea is really simple. If I know the lensing, I can, or if I know some proxy for the lensing from large-scale structure, I can run this lensing in reverse. and then remove these sort of lensing B modes and reveal and restore the original pristine and clean B mode sky, hopefully. So this is something that I think a lot of us think is really interesting because it's so important, and so I've been working a fair bit on this recently, and I'll just quickly review some of my earlier work and discuss what I'm working on now. So a few years ago with Marcel Schmidtful, we realized that current lensing maps are just not good enough to do a great job at this. And so using a proxy from large-scale structure is actually much better. So we proposed using the infrared background as a proxy for lensing, and then run the lensing in reverse, and we showed that you can actually do a pretty good job, reduce the error by a fair bit. But part of the reason we thought this was cool is because no one had actually shown that this delensing stuff works in data. And we have the infrared background now. So something that I proposed to a really good graduate student, Patricia Larson, formerly at Cambridge, as well as Anthony Challoner, is to just try to show that this delensing stuff actually works in data for the first time. And so what we tried to do is delens not the polarization, which is the real problem, but the temperature, because it was a little easier to do. So the idea was we would take the Planck CMB temperature map, which has a bunch of lensing in it, and I've illustrated that by pressing something on a Photoshop thing. It's kind of blurred out. And we would take a lensing map from the infrared background, and we would run it in reverse. And if everything is working super well, what we should find is that we've removed this blurring. We've restored the really nice, unlensed, pristine and sharp CMB sky. OK, how do we check that we've actually done this successfully? How do we quantify this? Well, the way we quantify this is measuring the lensing, not the lensing power spectrum, but the temperature power spectrum, the standard CMB power spectrum. But even that shows you how much lensing is left. Because the more lensing you have, if you have no lensing, the peaks are as in blue. They're very sharp. But if I have a lot of lensing left, it's all blurred out, and the peaks are reduced, and the troughs are filled in. OK, so I can the difference between a CMB with lots of lensing and one that I've successfully delensed is in how sharp the peaks are. And so the statistic we looked at is the difference of these two. Have we delensed successfully? Well, if we have, what we should see in this difference statistic, which cancels cosmic variance, it's really a key point, is that this difference has this peak structure. Because a peak gets bigger and a trough gets deeper if you successfully unblur, right, and delens. And so this is what you expect. And after a lot of work on simulations, Patricia sort of looked at the data, and this is what we got. And so here, I think you can see very clearly that we have shown delensing. And most importantly, it's consistent with what we expect. Right? So the data agrees with our theory, and that gives us confidence that all these forecasts that we've been doing for a long time now are actually going to work. And there was a lot of great work after this by Julian Caron and the SBT team, and Alessandro Manzotti and others building on this. That's what we've done recently, showing that this works in these early demonstrations at sort of moderate significance and utility. Now we're facing the real problem, which is making this actually improving inflation constraints. And this is something that we're working on now with Simons Observatory. Julian Caron and I are trying to make this work in real upcoming data. The problem with Simons Observatory, when we first started looking at this, is it didn't seem all that promising. So if you just look at a lensing map from Simons Observatory, it's great, but it actually is still too noisy to really help you a lot. It only improves your constraints by something like 20%. That's why I drew a sad face. So what we're working on now is trying to not just use our lensing measurements internally from Simons Observatory, but we're trying to throw all the data that we have and that we're going to have at this problem. All right, so we're going to not just take the Simons Observatory lensing map, but we're going to co-add in galaxy surveys, such as the Dark Energy Survey galaxy distribution, or ultimately LSST galaxies. We're going to co-add those. we're going to add in the infrared background map. And we're going to build up this super correlated, awesome sort of lensing proxy that we can then use to de-lens. So that's the plan. And from super early forecasts, it looks like we can do a lot better. Maybe get a factor of 2 improvement on these inflation constraints, which might not sound like much, but that's like building another copy of Simons Observatory if we can do that. So that would be a big deal if we can get this to work. Of course, there's an enormous amount we have to figure out. We have some ideas of how you can marginalize over astrophysical uncertainty in an entirely agnostic way, but there's just an enormous amount of open questions, right? How do you both de-lens and foreground clean? How do those interface? Like, what's the order of operations, and how do you actually do this? What is the likelihood, especially if I have a bunch of astrophysical maps in there? How do we deal? What are the systematics? We really have no idea. So it's sort of a fun problem because there's an enormous amount we're still figuring out. But the hope is that with lots of work, we'll get this all to work, and for CMB stage 4, push even further down into this lensing noise. And ultimately, I think we can really improve constraints. But of course, the coolest thing would be if someone hands us a map full of lensing B modes, and we run our fancy de-lensing pipelines, and then we reveal a signal from inflation. So I think that would be the best case scenario. All right, so thanks very much for your attention. I hope I convinced you this is an exciting field. We have lots of data coming. It could be that there are new methods that will allow us to go even further, and this kind of science will allow us to determine a neutrino mass, help us probe inflation, and also map all the mass in the observable universe, or most of it, in the next decade or so. So I think it'll be really fun. Thanks.
Thanks, Mike, for a nice talk. Are there any questions? During the talk?
I have a question. So you quoted a limit of 30 MeV.
Mm-hmm.
You said it was Simons/S4.
Yeah.
So which is
That's a very good question. And was that? Well, it actually ends up not really being limited by the CMB experiments, right? And that's sort of why I did this sort of silly notation. The thing that really, what you're doing is you're measuring a suppression in the growth of structure, right? But then when you say a suppression, the question is suppression relative to what, right? And so you have to look at the suppression relative to something at high redshifts, and that you get from the CMB via knowing the optical depth, because you need to know how much it's scattered to figure its time. Yeah. So basically, this error bar is so big right now that, if it improves a lot, then there's going to be a big difference between Simons Observatory and S4. But it depends on what happens up there in the tau measurement. Yeah. Yeah.
How do you disentangle something like the suppression of the structure from like neutrinos? You mentioned the ASIA.
Yeah, that's a good question. I mean, to some extent, they're degenerate. But Renee is the expert on this. But I mean, the general idea is that they have different scale dependences. I mean, that's so you'll have a different L dependence. And so you can distinguish them to some extent. You can get even more distinguishing power by adding in cross correlations, right? Or adding in redshift dependences. And some of these effects, for example, dark energy, will have much less degeneracy with neutrino mass when I actually add the sort of time dependence in addition to the scale dependence. Yeah, so.
Things like H-notes.